students, in this lecture I am going to discuss about project scheduling, that is a PERT CPM. So, the agenda for this lecture is finding earliest starting and earliest finishing time of activities, that technique called forward pass. The reference for this lecture is from the book Anderson et al. Managers are often responsible for planning, scheduling and controlling projects that consist of numerous separate jobs or tasks performed by a variety of departments and individuals. These projects are often so large or complex that the manager cannot possibly remember all the information pertaining to the plan, schedule and progress of the project. In such situations, the program evaluation and review technique called PERT and the critical path method CPM have proven to be extremely valuable. What are the applications of this PERT and CPM? PERT and CPM can be used to plan, schedule and control a wide variety of projects. Common applications include research and development of a new product and processes, construction of plant, building and highways. Another application is maintenance of large and complex equipment, and another application is design and installation of new system. Like this, the concept of PERT and CPM is having numerous applications. The various jobs or activities required to be done to ensure the entire project is completed on time could be often be interconnected with each other. For example, some activities depend on the completion of other activities before they can be started. Because projects may comprise as many as several thousand activities, PERT and CPM help project managers answer various questions. What are the typical questions that the PERT and CPM can answer? What is the total time to complete the project? It is a very important question. How much time it will take to complete the project? What are the scheduled start and finish dates for each specific activity? If a project has n number of activities, you should know when a project should be started, when an activity will end, when a activity should be started, when an activity will be finishing. So, which activities are critical and must be completed exactly as scheduled to keep the project on schedule. So, that activities are critical activities. Later we will be studying if there is a small delay in critical activities, that will affect or that will delay the whole projects. So, that activities are called critical activities. How long can non-critical activities be delayed before they cause an increase in the total project completion time? There may be some non-critical activities, there will be some allowable time that that activities can be delayed, but there is a limit for that delay. So, beyond certain point, even the non-critical activity may affect your total project completion time. So, these questions will be answered with the help of this project network, that is called PERT and CPM. When you look at this origin and history, although PERT and CPM have the same general purpose and utilize much of the same terminology, the techniques were developed independently. PERT was developed in the late 1950s by the Navy, specifically for the Polaris missile project to handle uncertain activity times. This is one important difference between PERT and CPM. In the PERT, this activity duration is uncertain. Whenever any new projects, very innovative projects, it is very difficult to exactly estimate time taken to complete an activity. So, whenever there is uncertain in the activity duration, we should go for PERT. CPM, critical path method, was developed originally by DuPont and Remington Rand primarily for industrial projects for which the activity times were certain. Here, so it should be very important, these activity times were certain for CPM, the activity time is uncertain for the PERT. And when you look at the CPM, since the activity time is certain and the variability was not a concern. Critical path method offered the options of reducing activity times by adding more workers and or resources, usually at an increased cost. Later part of the time we will be studying a concept called crashing, where we will be using the concept of linear programming. There will be I will introduce the solver. Okay. So, that we will be studying, we will be studying after some time. Thus, the distinguishing a feature of CPM was that it identified trade off between time and cost for various project activities. When we look at the modern interpretation, today's computerized version of PERT and CPM combine the best features of both approaches. Now, the distinction between the two techniques is no longer necessary. Now, I am going to take one example. That example I have taken from this book called Anderson et al. Project scheduling based on expected activity time. When I say expected activity time, we can say average activity time. Suppose activity A, okay, for example, event A and event B. So, this is an activity. Here, so for example, 5, the average activity time is given. Okay. The owner of a shopping center plans to modernize and expand the current 32 business shopping center complex. The project is expected to provide room for 8 to 10 new businesses. The first step in the PERTCPM scheduling process is to develop a list of activities that make up the project. So, the first step is we have to identify the list of activities that is required for completion of the whole project. So, this table provides all the activities for the shopping mall project. There are 1, 2, 3, 4, 5, 6, 7, 8, 9 activities there. Each activity description is given. First activity A, prepare architectural drawing. After that, immediate predecessor, there is no immediate predecessor, and for that activity the expected time is 5 units. It may be day or any units. Like this, activity B, identify potential new tenants. C, develop prospectus for tenants. So, for this there is an immediate predecessor. So, activity C can be started after completion of activity A. Similarly, for activity D, select contractor, that can be started after completion of activity A because it is a predecessor. Similarly, for activity E, prepare building permit, that also can be started once you complete the activity A. That is why these 3 activities C, D, E having activity A as a predecessor. Similarly, activity F, activity G has having 2 predecessor D and F, and activity H having 2 predecessor B and C, activity I have another 2 predecessor. When you add, when you sum this all the project duration time, it is 51, say I think the unit is weeks. So, what will happen, when you do all the activities one by one, it will take 51 days, that is the sum of expected activity time is 51. As a result, you may think that the total time required to complete the project is 51 week, but that is not correct, because here what we can do, 2 or more activities often may be scheduled concurrently, assuming sufficient availability of other required resources such as labor and equipment, thus shortening the completion time for the project. It is not necessary it will take 51 weeks. Certain activities can be done parallelly, so that it can be finished less than 51 weeks. The activities correspond to the node of the network. Okay. Here we are node we represent in the form of rectangle, and the arc. So, if I say it this way, like this, and the arc, this one shows the precedence relationship among the activities. In addition, nodes have been added to the network to denote the start and finish of the project. The node represents, for example, this activity, if I say A, this is start of that activity A, this is node. Okay. 2 is another node, the activity is A. There is a distinction between node and activity. Activity will consume time, consume resources, but node is just to indicate when this activity started or when the activity will be finished. A project network will help manager visualize the activity relationship and provide the basis for carrying out PERT CPM computations. So, all the activities can be represented pictorially considering various precedence constraint. So, that picture is nothing but your project network. Look at this, this is the project network. There is a start, I have given C activity A, B, C, D, E, F, G, H, I, at the end there is a finish. Project scheduling based on expected activity times. To facilitate the PERT and CPM computations, we shall modify the project network as shown in the next slide. Note that the upper left corner of each node contains corresponding activity letter. So, what we are going to write? We are going to represent like this. Okay. So, if I say A, this is upper left hand corner denote the activity letter. If I say some number, for example, here for activity A, how much time it is taken? Activity A is 5, say if I say 5, this is our activity duration, and the activity time appears immediately below the letter. Here what I am going to write? Here I am going to write earliest starting time, earliest finishing time. Here I am going to write latest start time, sorry, latest finishing time and latest start time. This is the notation which I am going to use. The first aspect is I need to know the critical path. So, to determine the project completion time, we have to analyze the network and identify what is called critical path for the network. What is the meaning of critical path? The activities in the critical path cannot be delayed. If any activity along the critical path is delayed, that will extend, that will delay the whole project completion time. So, what is a critical path? A path, when I say path, is a sequence of connected nodes that leads from the start node to finish node, that is a path. All paths in the network must be traversed in order to complete the project. So, we will look at for path that requires greatest time. So, the path which requires the greatest time is called critical path. Because all other paths are shorter in duration, this longest path determines the total time required to complete the project. If activities on the longest path are delayed, the entire project will be delayed. So, the longest path is called critical path. Activities on the critical path are referred to as the critical activities for the project. Now, I am going to explain. To find out the critical path, you should know the earliest time for any activity. It may be earliest starting time or it may be earliest finishing time. The ES represents earliest start time of an activity, EF represents earliest finish time for an activity, T is expected activity time. So, the earliest time for any activity is earliest finish time is for any activity is earliest start time plus the duration, that is expected activity time. Now, I am going to explain what is this forward pass. Activity A, when you look at this activity A, the expected activity time is 5 weeks. So, the activity A can start as soon as the project starts. So, we set the earliest start time for that activity is equal to 0. Suppose if I write this way, so the earliest start time is 0, I am writing this way, and the earliest finishing time is 5. How I got 5? 0 plus 5 equal to 5. So, we will write the earliest start and earliest finish time in the node to the right of the activity letter. So, I have written this way, this is the way we have to write the. So, this represents this earliest start time, this represents earliest finish time, EFT. Using activity A as an example, you see A, the activity duration is 5 weeks. So, earliest start time is 0, earliest finishing time is 5, because 0 plus 5 equal to 5. Like this we have to write for all activities. Now, I am going to explain what is this forward pass. Because an activity cannot be started until all immediately preceding activities have been finished, the following rule can be used to determine the earliest start time for each activity. What is that rule? The earliest start time for an activity is equal to the largest of the earliest finish time for all its immediate predecessors. So, what will happen? There may be a situation, like this. Suppose I am writing this way. So, what is the meaning? Suppose here the earliest finishing is 5, here the earliest finishing time is 6. Okay. Now, suppose assume that these are predecessors. Okay. Here the earliest start time is nothing but 5 and 6, which is larger, 6 is the larger. So, 6 means that earliest start time, that is the meaning. The earliest start time for an activity is equal to the largest of the earliest finish time for all its immediate predecessors. So, there are 2 predecessors. So, the largest of this earliest finish time is 6. So, this 6 should be the earliest start time for the succeeding activity. That is the meaning of this forward pass. Let us apply the earliest start time rule to the portion of the network involving A, B, C, H. A, B, C and H. We know that this is earliest start time is 0, earliest finish time is 5. For B also earliest start time is 0, earliest finish time is 6. Okay. For C, the earliest start time is 5, the finish time is 9. Okay. Now, for the activity H, there are two earliest finish time, one is from activity C and activity B. So, for activity C the earliest finishing time is 9, for activity B the earliest finishing time is 6. So, the earliest start time for activity H will be 9, 9 plus 12, 21. Okay. So, that is that is what I have written in the text. For B I have written 6. When you look at C, looking at node C, we note that the activity A is the only immediate predecessor for activity C. So, the earliest finish time for activity A is 5. So, the earliest start time for activity C must be 5, that is I have written here 5. Thus, with an activity time of 4, the earliest finish time for activity C is 9. So, 5 plus 4 is 9. So, for activity C the earliest finish time is 9. Now, we look at the node D. So, node D, in node D the earliest finish time of activity A is 5. So, the earliest start time for D must be 5. Okay. So, there is duration is 3. So, 5 plus 3 is equal to 8. So, earliest finishing time for activity D is 8. Now, look at the node E. Here it is 0, it is 5. We note that the activity A is the only immediate predecessor for activity A. So, the earliest start time for the E is 5, this duration is 1, 5 plus 1 it is 6. Looking at node F, we note that the activity E, this activity is the only predecessor for activity F. The earliest finish time for activity E is 6, this 6. So, the earliest start time for activity F must be also 6, and the duration of this activity F is 4. So, the earliest finish time will be 6 plus 4, 10. Now, look at the node G. The node G, we note that activities D and F are immediate predecessor for the G. So, what are the earliest finishing time for activity F and D? So, here 0, 5, 5, 6, 6, 10, 5, 8. So, the earliest finish time for activity D is 8, for activity F is 10. So, the earliest start time is the larger value of 8 and 10, which is 8, which is that is the 10. So, 10 will be your earliest start time for activity G. So, with the activity of 14, so earliest finish time will be 10 plus 14, it is 24. Why I am saying forward pass? See, I am going this direction, it is called forward pass. When I go from left to right, whichever is the larger earliest finish time, that should be the earliest start time of the succeeding activity. Now, moving on activity H. This activity H, there are two predecessors, one is C and B. For B, the earliest finishing time is 6. For C, the earliest finishing time is 6. So, the 9 is the earliest finish time for activity C. So, we select larger value, that is between 9 and 6. So, 9 is larger. So, 9 will be the your earliest start time for activity H. So, 9 plus 12, 21 will be your earliest finish time. Now, looking at the node I, when you look at node I, there are two predecessors, one is H and G. Now, we have to see which is the largest earliest finish time between H and G. What are they? So, the earliest finish time for activity G is 24, for activity H it is 21. You see this is 21, this is 24. Which is the largest one? 24 is the larger. So, 24 will be the earliest start time for activity I. The duration of this activity I is 2. So, the earliest finish time will be 26. So, what I am going to do now, I am going to write all the earliest start time, earliest finish time at a stretch. So, this is A is not having any predecessor. So, it is 0, here also it is not having any predecessor, it is 0. So, 0 plus 5 it is 5, here 0 plus 6, 6. So, the earliest finish time of activity A will be the earliest start time for activity C. So, 5 plus 4 9. So, here 5 plus 1 6. Okay. So, 6 plus 4 10, here 5 plus 3 8. So, the larger one is 9 plus 12 is 21. Here the larger between F and D, the larger one is 10, it's 24. So, between 21 and 24, 24 is the larger one. So, 24 plus 2 is 26. So, the total project completion time is 26. So, the earliest finish time for activity I is the last activity in the project is 26 weeks. Therefore, we know that the expected completion time for the entire project is 26 weeks. This we have arrived with the help of a technique called forward pass. So, in this lecture I have explained about finding earliest start and earliest finishing times using the technique called forward pass. What is that forward pass? If there are two predecessors for an activity, so the earliest start time for that activity is the largest finishing time of the previous two activities. So, that is the technique called forward pass. In the next lecture, I will discuss about the backward pass. Thank you.